Thanks for inviting me. Always a pleasure to talk about the next steps in AI. And as Hugo said, AI in its simpler forms, which are not necessarily all that simple, is now having huge successes all across business. So the value of AI for the practical business of technology is no longer in doubt. But I think that we're in a transitional period now, and you can phrase that in many different ways. The language Hugo used was weak AI versus strong AI. I often talk about narrow AI versus AGI, or artificial general intelligence. And yet another way to look at it is what I put in the subtitle here. So current deep learning algorithms are very powerful, and they're very good for certain types of applications. On the other hand, there's a certain type of understanding. There's a cognitive aspect that they lack. So I think we're moving now from weak AI, narrow AI, and highly specialized deep learning networks and expert systems gradually toward AI systems with a greater and greater degree of general intelligence and more understanding of context, more ability to generalize from one context, situation, or problem area to another. So I'm going to talk a little bit about these ideas from a general point of view, and then share some experiences with specific projects that I've been working on that are sort of in this transitional border between narrow AI and more general AI. The term AI is a confusing one. I've written a bunch about it. I'm not going to be able to fully clarify it here. I mean, in a way, both the term artificial and the term intelligence are problematic, because, I mean, it's an AI is it's an artifice in a sense, but it's a natural system, and it obeys the laws of physics. And as AIs get smarter and smarter, they're not going to be anyone's artifice or tool. They're going to be their own minds. And on the other hand, the concept of intelligence is also somewhat vague and hard to measure. IQ tests don't even work across different cultures, let alone across different species or types of minds. Nevertheless, AI is a term everyone recognizes now from science fiction, if from nowhere else, and it's what we have to work with. The way I think about the concept of intelligence, which was a controversial way to look at it a few decades ago when I entered the field, and it is much less so now. I think about an intelligence as a pattern recognition system, but critically, it's not just recognizing patterns in perceptual data, it's recognizing patterns in itself. It's recognizing patterns regarding which actions will be likely to achieve what goals in what contexts. And it's always doing so with limited energetic resources and limited amounts of time. And the role of resource limitations in AI is quite important. I mean, the German AI theorist Markus Hutter, who's now at Australian National University, he showed how you could build an essentially infinitely intelligent artificial intelligence in like 50 lines of Lisp code. Now, the problem is it would use more computing power than we have available in the observable universe, right? But it's a very nice piece of mathematics, and it gets across a conceptual point, which is that, real world AI, in the end, it's all about how do you balance different resource limitations against each other. I mean, that's where all the complexity comes from. Recognizing patterns in what actions will achieve what goals in what contexts in real time using limited resources. And that relatively simple specification leads to an awful lot of complexity, like the complexity inside each of our heads and the complexity of the AI systems that our group is building and that others are building. The distinction between narrow AI and general AI, it's not a completely crisp distinction. There are many things in the border between them, but I think it's a very useful distinction nevertheless. And you can see that when looking at the scope of AI applications that have been successful recently, because in each case, these AI systems are configured very specifically to do very particular things. And when you stretch them beyond the very exact context they were designed for, they basically can't do anything. And human beings are quite different from that. I mean, you can put a human in a situation that they had no explicit training for and that didn't exist when they were created, and we can kind of muddle through and gradually learn how to operate in a new environment. So one example of this pertains to AlphaGo, the Go playing system we've all heard of. I mean, if we want to play Go on this board, now I'm a pretty bad Go player, but my limited knowledge of Go I could transfer to a funny shaped board. Now, a champion Go player could play very, very well on a funny shaped board, even though some of their knowledge would not apply. AlphaGo simply cannot play on the funny shaped board because there's some code in there that defines a Go board as a 19 by 19 array, right? Now, of course, a human could go in there and reconfigure that, but that's like applying brain surgery to a human Go player, right? What you want is for the game to be represented at a more abstract level. And representation at a more abstract level enables generalization to more different contexts. So, of course, if the problem were to play Go on any polygonal 2D board, you could program software to do that. But then when you have a program on a torus or introduce 3D Go or red, white, and blue different tokens or something, then again you'd have to reprogram the AI to do that. And self-driving cars, obviously, they're narrow in a very strong sense. I mean, if you take current self-driving cars and put them on the streets of Addis Ababa or Karachi or put them on a mountain road, they're not going to do it because there's all sorts of specializations made inside that software, which isn't bad from a product engineering point of view. It just means that we're building very narrowly defined system, and you could see that in a striking way with one of the crashes that occurred with a Tesla in the U.S. a few months ago. I mean, what happened there? Some guy was driving down the road, and he was doing what he's not supposed to do, which is just ignoring the road and playing with an electronic device and just letting the car drive instead of just assist him. And then some big white thing came across in front of the car, and it just drove into it. Now, what happened there? I mean, if you dig into it, there was some deep learning model that was trained on certain obstacles in front of the car, and the actual obstacle that emerged in front of the car just wasn't recognized by these trained models because it was different than what was in the training data, right? Now, of course, they can solve that problem by adding more and more stuff to the training data, and it's arguable, maybe even with these occasional errors, still having the automated system drive is safer than a person driving. But nevertheless, that sort of thing highlights the value of being able to generalize. Like in that case, it's a pretty simple generalization. There's some large mysterious object which appears to be in front of me. Maybe I should stop or go out of the way, right? And I mean, humans sort of have that common sense from a lot of different situations. And a deep neural net, which is basically operating as a nonlinear regression algorithm trained on a certain body of training data, it doesn't have that sort of intuition. So this notion of general intelligence achieves the ability to generalize to different contexts than the ones the system was programmed or trained for. I've been flogging this idea for 15 years or so now, and since 2006, we've been having research conferences on this each year. The next one is in August in Melbourne in Australia, in case anyone wants to come. These are a mix of academic and industry people. It tends to be somewhat theoretical, but some cognitive science, some neuroscience, and some practical stuff also. The goal of building artificial general intelligence is very nice, but having the goal doesn't tell you how to do it. And of course, this was the goal of the original AI researchers back in the 1940s and 50s. In fact, the idea that narrow AI exists was not obvious back then, right? That in a way has been a major discovery that, hey, we can achieve these things that seem to require great general intelligence by people by a bunch of relatively simple tricks, and that wasn't obvious from the get-go of the AI field, and it was interesting. But having discovered that, we can also now see the limitations of that kind of approach. So a number of us are pursuing more ambitious approaches to AI and trying to explicitly build artificial general intelligence. The OpenCog system is an open source project which is based on some ideas about building AGI that I developed together with a number of long-term colleagues. The ideas and algorithms underlying OpenCog are sketched in this pair of books, Engineering General Intelligence, Part 1 and 2. Now, my oldest son, who's a computer science grad student in Copenhagen University, he says these books are sort of like the summary abstract of the OpenCog approach, which is somewhat scary because there's 1,000 pages there. But I mean, building a thinking machine is hard. And if you look at a neuroscience book, it's a lot fatter than that. And that's the summary abstract of how the brain works. So there's a lot there. The book AGI Revolution is a bit less technical and gives a summary overview of our perspective on how to build AGI. Or if you prefer to read Korean, there's a version called AI 2030, AI Revolution 2030. So the Ray Kurzweil forecasts human-level AI in 2029. Now, my Korean co-author, Young-Suk Park, thinks that's too optimistic. So she wants to be more conservative. She's upped it to 2030. Or maybe it means it'll take a year to get from Silicon Valley to Korea. I don't know. So OpenCog, it's quite complex. I'm just going to give a capsule summary here. Rather than a neural network, it's a more general type of network. It stores knowledge as a weighted labeled hypergraph. So it is a network. It has nodes and links. It has many types of nodes and links. And in essence, we can represent logic programs or functional programs or basic empirical data items using different node and link types within the same network, which is a fairly complicated thing to do. You get a big, complicated network with a topology that depends on what kind of data is in it and what you're doing with it. And there's then a bunch of different cognitive algorithms that act on this same network. We have a logical reasoning engine called PLN, Probabilistic Logic Networks, that acts on nodes and links representing declarative knowledge, conditional probabilities, quantifiers, and so forth. There's an evolutionary learning algorithm that tries to learn new procedures and new concepts. There's activation spread around the network, sort of like in a Hopfield network, an old style attractor neural network that regulates the flow of attention. There's a goal system where the system can then learn sub-goals to its goals. So there's a lot of different things. And if you're old enough like me, you'll remember something called blackboard architectures in AI a really long time ago. And this is a bit like that. I mean, the atom space, the way it labeled hypergraph, is like a blackboard. And there's multiple different algorithms reading to and writing from this hypergraph at the same time. And of course, the hypergraph itself can span multiple machines and multiple cores and so forth. We've used this within vertical applications in a number of different areas, and each one has been a fairly complex custom job so far. We've used it for stock market prediction based on quantitative data, news, and fundamental information. We've used it in biology, for instance, to understand genetic underpinnings of Parkinson's and Alzheimer's and longevity based on in the case of Parkinson's, it was looking at mutations in mitochondrial DNA, but the strength there is it can look at sort of low-level biological data in the context of the whole biological system and biological ontologies and so forth. I've been working with a company called Hanson Robotics, which has made some amazingly realistic-looking robots. I'm short on time, so I won't go through it fully, but that's Sophia, which is that's a human, I think. I've never that's a robot. Yeah. So that's resurrected Albert Einstein, of course. Yeah. So these are very, very realistic looking robots. Actually, we had one performing at a music festival in Hong Kong not long ago. So well, it was cool because many people in the audience did not quite realize it was a robot. I mean, granted, they were all very drunk at the time, which helps. But I mean, there's a lot of weird people on stage at a music festival. That's it. So about the head movements, again, we can get head movements to be sort of realistic looking by using a deep neural network to simulate, to measure head movements of a person using motion capture. Then you can generate head movements by instance generation from that distribution. Then you get something that's quite realistic, more so than just programming. And you have a lot of funny robot videos, but not much time. Telepathy transmitter wired within your skull. It keeps us constantly. So they're definitely not yet to human level intelligence, but we can feed in a bunch of data and it tries to generate sensible things based on the context of what you're saying to it. Here she was claiming she could read my mind, so somehow reality cannot be detected. Now, how she figured out, I don't know. I didn't tell her that though. That's like self-generated, which is interesting. So, for this application, for Hanson Robotics, it's been quite complicated. I mean, we have OpenCog, which is doing some reasoning and learning. We're using a whole bunch of open source deep neural nets customized but for visual perception and auditory perception. Then OpenCog is instructing what actions to do, but then the specifics of moving the motors in the robots is done by separate code outside OpenCog at the moment. So that this has been an interesting exercise in hybridizing OpenCog for language processing and symbolic understanding with deep neural nets for perception processing and then for movement control also. And this is a research area we've been getting into quite intensively because OpenCog can, the weighted labeled hypergraph semantic representation, it can't yet scalably deal with like high volume floating point data. On the other hand, deep neural nets can't yet abstract very well and they can't explain what they're doing. So finding the right ways to connect these together has been interesting and important. So from a research standpoint, we're looking to use this to really make thinking machines, like in the grand plan of AI. And I mean, we're still now at the stage of trying to get a system with what I'd call basic sentience, where it can just understand the world as well as a 3-year-old child or retarded human could, for that matter. So now these systems are sort of idiot savants, that they have a very crude common sense understanding of the world coupled with very refined specialized analytical or inferential capabilities. Once you get to a system that has a basic understanding of who and what it is and what it's doing in the common sense human world, then I think you can quite rapidly proceed through the next stages. I mean, not minutes, but years, right? So once a robot could sit here in the room, understand it's sitting in a conference room with a bunch of IT professionals, know who it's met, who hasn't met, know this thing is going to last a few hours, then everyone will leave. Once it has a basic understanding of itself and its situation, then you can start to teach an AI the way you teach a young child. And then its common sense knowledge can start to synergize with all this expertise that it has to do calculations and make inferences and recognize patterns in data. So the grand plan with which we founded the OpenCog AGI project was sort of to progress through phases from basic sentience to being an artificial school child and eventually being a genuine expert rather than a brittle expert system. Now, that's going to be a lot of work to get there. So what we're doing is applying the OpenCog platform to solve various practical problems that leverage important capabilities. and building out the system bit by bit, application by application. So I've mentioned a bit the role of deep neural nets and the hybridization of those with OpenCog. I'll talk about that for a couple minutes now because I know Hugo and a bunch of others here have been applying deep neural nets in practice. So just to set the context, this is the human brain splattered out in a particular diagram. Each of these boxes is a region of the human brain identified by neuroscientists. This is sort of the connectivity between regions of the human brain. And each of these regions carries out many, many different functions, most of which are not understood. By comparison, current deep neural nets, while interesting, they're pretty much based on models of a few different regions of visual cortex, and mostly the feed-forward activity, not too much feedback activity yet. So it's very interesting to be inspired by aspects of what the brain does. On the other hand, the brain does a lot more than recognize patterns in hierarchically structured schemes of data. And that's not a particularly new observation. For example, the differential neural computing, last year, it doesn't seem recent in the context of deep learning because there's like 100 papers every day, but it was maybe 6 months ago or something. What DeepMind did is they took a typical deep neural network hierarchy and they put it together with a sort of memory matrix which simulates part of the hippocampus, or part of what the hippocampus does. They showed that could learn to navigate in maps and do various things that a typical deep neural net cannot do. And that's interesting. It's a significant step forward. On the other hand, you're taking part of visual cortex and you're connecting it with one aspect of what hippocampus does. But there's so much else going on in different parts of the brain. There's so much complexity going on there. I mean, and none of this sort of thing is capturing what's happening with long-term memory, metacognition, emotion, just deliberation and reasoning. There's a lot going on which is studied in cognitive science. It's not in these relatively simple systems. So one approach you can take is just take that neural net, take that neural net, next year add another one, next year add another one, and maybe in 10 years, DeepMind will have 50 different neural nets emulating different aspects of what different parts of the brain do, and you can try to backpropagate on all of them and try to get it to be generally intelligent. I mean, it's not a stupid thing to do. Another approach is to look at the different kinds of cognition that the human mind can carry out and figure out how to carry out each kind of cognition using some computer science algorithm without worrying about exactly how closely it's inspired by the brain, and then have more of an integrated computer science point of view, which is more the approach we've taken in OpenCog. Not so much because I don't like the brain. I mean, I'm glad to have one, but I think in my view, we don't know enough about the brain to really model an AI algorithm and architecture on the brain in detail. There's just so many unknowns in neuroscience. And on the other hand, if you do succeed in emulating a human brain in detail, then all you have is a human brain. And I mean, a human brain cannot understand the structure of the internet or even a large computer network that Cisco might build. Human brain is very bad in understanding all the levels of the human body and how they interact. So not only don't we know how the brain works that well, but many of the things we care about are things the human brain is quite poor at doing, which is another motivation to use computer science algorithms that are better than the brain in some way, but connect them in a way that lets them emulate the common sense capability that human brains are so good at. And one part of that quest is being able to bridge the gap between deep learning algorithms and symbolic reasoning algorithms, like bridging the gap between sub-symbolic processing of sort of high bandwidth floating point data with symbolic logical manipulation. And what we're doing there, we're taking a certain type of deep neural network and we're connecting it with OpenCog, with its ability to do symbolic manipulation on these hypergraphs. And then there's a lot of detail that you have to deal with to make that work. Because most deep neural networks, it's very hard to extract symbolic information from them or inject symbolic guidance into them. We've worked out a sort of hierarchy of infoGAN networks, which will mean something only if you've played with deep neural nets a bit. But we took a certain deep neural net from the literature, which is good at exporting a sort of high-level summary of what it's doing, and we stack a bunch of those together, and we've designed our own variation of deep neural nets, which it's relatively easy to extract symbolic relationships from. So if that deep neural net is looking at your face, it can recognize there's eyes and a nose and mouth there, can export the locations of eyes, nose, and mouth, where those are concepts it learned from image analysis. You didn't tell it that. Can export the relations between eyes, nose, and mouth here. Then OpenCog can reason about that and can observe, like, oh, sometimes people have these glasses on their eyes, sometimes they don't. They're more likely to put them on when they have to read something, right? So for OpenCog to make that reasoning, it needs to get a sort of high-level summary out of the deep network. So getting these two kinds of AI thinking to work together is one part of the larger prospect of building an integrated computer science system that can achieve general intelligence by basically putting different algorithms in each of the boxes regarding the high level cognitive capabilities of the human mind. So yeah, some of the key strengths of this sort of integrated architecture would be it's not just designed for task-specific problem solving. It's designed to operate in autonomous or semi-autonomous agents, since this, after all, is what the human cognitive system is designed for. And we're taking our high-level architecture from human cognition and trying to achieve each thing the human mind can do using different computer science algorithms. It's designed to operate in unpredictable, open-ended, unforeseen environments, and we're inspired by human cognition, including areas where we don't know how the brain achieves a certain function of human cognition. We can still look at what kind of thinking needs to be done. By not trying to hew that closely to what the brain does, we can take full advantage of modern computing technology, which on the hardware level is not especially brain-like. And we can put together big data learning with small data learning. I mean, the mining patterns from big data is super valuable, and many machine learning algorithms, deep neural nets, but also support vector machines, evolutionary learning. Lots of these algorithms are way better at mining patterns from complex big data than people are. On the other hand, we can often learn something from one example, right? And that's because we're bringing all this contextual background knowledge into the learning process. Now, we can also sometimes be wildly wrong in doing that, but we can do it better than any current statistical machine learning algorithm. And bringing this sort of intuition and context-based small data learning together with sort of inductive pattern recognition-based big data learning, that's a very important combination to get right. And I think we're starting to do that in OpenCog, and we're working on that more and more. Now, I've used up almost all of my time, so I'm going to skip the last bits of this, but let me briefly tell you what was in there anyway. So
that is like the whole underlying point of all the different sessions, is to think about the impact on the infrastructure, right?
yeah.
So it's up to Hugo, but if you want to let you.
No, please. Yeah.
Okay, I go a couple more minutes.
Question and answer. So.
Okay,
Yeah.
I go a couple more minutes. Yeah. So actually, I don't know that much about networking, so I'm not going to have that much to say about that. But I have, since moving to Hong Kong 5 years ago, I've gotten to know more and more about hardware, which wasn't my background. Originally, I had a PhD in math, and I was an academic in math and cognitive science. But I've dug fairly deeply into, with some engineers who know much more about it than I do, what you would do to make chips and processors that are good for AGI. And it's a little bit different direction than deep neural nets. What you find when running this kind of AI algorithm is almost all your time is spent putting stuff in and out of RAM. So you got this big graph in RAM, and you're doing sort of hard to predict small reads and writes on this large graph. The cache system of standard processors isn't incredibly useful because you don't have that much determinism in predicting what you're going to want next based on what you got before. Certainly, you can use multiple cores quite well, and you're going to need multiple machines. You also have a mix of SIMD and MIMD parallel things, because like spreading attention around in the hypergraph, I mean that's very much SIMD parallelism. That's just like a neural net, and some other shallow kinds of pattern recognition can be like that. On the other hand, if you're doing logical reasoning, you're doing sort of backward and forward chaining inference. That's extremely hard to boil that or most complex graph operations down into SIMD operations. You really want just multiple independent processors. Also, even though you need to spread your graph across multiple machines, the graphs we care about never partition into nice clusters. So you just have a big messy graph that you need to spread across different machines. Now, there are machines that are good at this kind of thing, like this Eureka from Cray is very nice. Unfortunately, it's very costly, so it's irrelevant to pretty much everything that we're doing, except it shows that people can optimize hardware for large graph operations. I mean, the intelligence community in the US uses many of these to manipulate graphs for good reason. Now, Intel has stepped in this direction a bit with Xeon Phi, except it's essentially an unsupported piece of hardware. Like there's no software libraries for it. Although it's very nice, you've got like 70 MEMD processors and get a few gigabytes of RAM they can act on. So it was a nice piece of hardware, which in principle was going in the right direction. Now, another interesting hardware company is Venray Technology out of Texas in the U.S. They're not doing MEMD parallelism, but what they do, they just put processor and RAM right on top of each other. So you have incredibly fast access to RAM, because I mean that's all circuitry. They're just right in the same place. So they believe this will completely obsolete Intel, which may or may not, or maybe Intel will buy them, or who knows what will happen. But if you look at the recent batch of neural net chips, a lot of what's important there is just having processing and RAM in the same place, rather than being a neural network. I mean, being a neural network is nice for some algorithms, but putting processor and RAM in the same place is quite fundamental. And thinking a little more laterally, there's a project Ramplas in Holland, which is building optical RAM, and they have it's an academic prototype, but they've built optical RAM, which is quite fast and it's quite interesting. So if you think about 5 or 7 years from now, what would we really want for an AGI? I mean, optical RAM, SIMD and MIMD processors like right on top of the optical RAM, right? Then you're going to be 1,000 to 10,000 times faster, and then you need a nice like optical processor interconnect between these things in your distributed system, and then there you go, right? And it sounds wacky now. On the other hand, I mean, 15 years ago, GPUs would have sounded pretty strange, and now they're in everyone's phone and in people's watches and so forth. So I think that's the kind of direction we're going to want to go in for doing advanced AI on large graphs. And what's interesting is it's pretty different than the direction of making faster and faster GPUs. And I mean, I see it like in China alone, I've seen like 10 startups making deep learning chips, which are, because basically you take a GPU and you modify it a bit to be optimized for neural nets rather than shading and texture mapping and so forth. And it's cool. These things are all good. On the other hand, it's a very specialized direction of hardware design. It's not necessarily solving the hardest problems. It's solving perception. It's not solving the problem of making a hardware architecture to deal with cognition. And we've thought a bit about how you would modify OpenCog to work on such a chip, although since we don't have the chip, we haven't written code yet. But it's designed well enough, I believe, that the cognitive code will be the same, And say we have a tool called the pattern matcher, which works sort of like a probabilistic version of Prolog or Datalog or something with some functional programming in there. So you specify a pattern with some blanks in it, and kind of like a SQL query, it tries to match that against the OpenCog atom space. And you could leave our pattern matching queries exactly the same, and you just change the engine that matches them to use your MIMD parallel thing. And I think for OpenCog, as an example, you could leave all the high-level code identical, and you're just changing the low-level data access and pattern matching mechanisms, and you could run everything on this sort of hardware, which will be super interesting. Now, whether you need to do that to get to a thinking machine isn't entirely obvious. I would like to think you don't, but I tend to be an optimist. So, I mean, what we can do now without this special hardware, much like with deep learning before you had GPUs, I mean, you can refine the algorithms, you can do a lot of interesting applications, and to do a really complex application now may require a bunch of different hardware. Once the hardware comes along in a more specialized way, the things we can do today with a server farm we'll be able to do on the phone that has the AGI chip in it, right? Oh, I think there was more. It's disappeared. I had a couple of slides that disappeared, which were about implications for networking, which were not as in-depth as these, but in looking at everything that was going to be presented at this overall symposium, including the stuff in the morning, which I didn't see because I was in another meeting, I was intrigued by the depth of thinking and prototyping on information-centric networks, for one thing, because it really seemed to me that in the ultimate extension, to make an ICN, in essence, you're turning the internet into a giant OpenCog atom space. I mean, it's kind of the same thing. What you want is the internet to be a giant content addressable memory, right? I mean, you want to have a layer where you can look things up based on what they are and what the information is, rather than on their address. And then if you want to do sort of dynamic caching of services, in the end, what you want is to take a complex process and split it up into many different parts based on information sharing requirements. And that's very much like what we need to do inside OpenCog when we have a cognitive process split among different nodes and links, which we may need to put on different machines. So, I mean, I came to the conclusion that in the end, to fulfill the vision of information-centric networking, almost the self-organizing intelligent network almost becomes the same field of study as making an AGI system, but there's a lot of strange complexities there, because you have a network where the higher level cognitive processes aren't supposed to know all the information that they're thinking about and passing around, which is subtle. But anyway, there's a huge amount of cross-pollination there, which should be interesting to pursue in the future. What Hugo and I have been talking about are more immediate term ways that the ability to combine symbolic reasoning with scalable deep learning could benefit Cisco is doing. And I think there's a huge amount of those in terms of using AI to understand the state of a network and summarize semantically what's happening in a complex network, as well as the ability just to understand specific kinds of data occurring in a network, be that video data or language processing data. But each of these projects, using hybridization of deep learning and symbolic reasoning to understand and communicate different aspects of what happens in a network. I mean, in the end, these all will build up to be part of the mind of the information-centric network, I guess. And then you have sort of minds within minds, because you have this ICN cognitive system, which is regulating and distributing the activity of the cognitive systems that are at the nodes and distributed among the nodes. So it's quite interesting, and that's an aspect I hadn't thought much about before seeing the various talks here. So, all right.
Thank you.